Because we always parse smoke programs before we interpret them, there's a whole class of errors that interp doesn't have to deal with. For example, if you start with the program text 1 plus 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 2, we don't have to talk about what interp would do with that because it'll never get past the parser. The parser, by converting the text into our abstract syntax, rules out a whole class of errors. A type language takes that a step further. It adds an extra layer of checking after parsing before interp to make sure that certain bad things won't happen. For example, that a number will never get added to a function. It's not that something comes out of check that interp needs, just that we will only call interp if we first called check to make sure that the program is okay. This has a couple of benefits. The main one is that the programmer gets a guarantee that certain things will not happen in interp. If it got past the checker, then it will be not possible to get a number added to a function in interp. But there's also a benefit to the implementer of interp, which is you don't have to handle the possibility that plus receives a number in function and decide what to do with it. The checker will rule that out. Now notice the second one especially only works if check is not implemented by calling interp. That is, we need to provide some guarantees about programs before we call interp, but not trying to use interp either. Otherwise, we don't get any benefits of the checker in the interpreter. As we go today, we're actually going to call check type check later, but for now, we'll think about just abstractly what it would mean to check something before we interpret it. Now, in the case of the parser, its checks are defined by a grammar. That is, we know which things are going to pass the parser because we've said, here's the grammar of the language. Maybe it has arithmetic and also multi-argument functions and if and booleans and so on, something else. But in any case, we write this down, and that's how we know what will work for parse. Can we do something like this for check? Like, clearly this happens before we interpret. It's some sort of check on the structure. Can we use a kind of parsing approach? And let's see what that means. So, for example, should check allow this expression? 1 plus 2. Well, it should allow 1 plus 2. That'll produce 3. We want to be able to do arithmetic and interp. Yes, that's something that should be allowed. So a number plus a number should be allowed. How about this expression? A function plus a number. This seems like exactly the sort of thing we want to rule out because we'll get not a number when we interpret right now, and that's the kind of error we don't want. So maybe the rule should be function expressions should not be allowed to the left of a plus, right? That's a rule that check could apply to an expression and disallow an expression that has that pattern. Okay, so function inside a plus, like to the left or right of a plus, not allowed. How about this one? Here we have the identity function first applied to 7. So we get a 7 back and then we add it to 5. So, well, if by not allowing function inside a plus we meant anywhere inside of the plus, then we would disallow this, which seems bad. I think we meant just immediately inside, right? Because this is really a function call immediately inside the plus with a function inside there. So, we'd get 12 if we interpreted this. Let's say we mean immediately inside. But now how about this one? So here again, it's a function call immediately inside the plus. We have functions nested more deeply in that. We want to allow functions and function calls, and yet if you run this, you've got the identity function added to 5. Because the identity function passed to the identity function will still be the identity function. So we don't want to allow this, but this rule about where you can put functions starts to get trickier. In fact, it starts to look like we just have to interpret things to decide what's going to be allowed, which would defeat the whole point. So we can step back and ask this theoretical question. Is it even possible to define well-formed, that is, things that would pass check, define well-formed in a way that rejects all programs that will ever produce errors? Okay, there is a smart aleck answer to this, which is yes, just reject all expressions, right? That way you'll never get an error because you're never allowed to call interp. But that's not good enough. Really, we mean, can we define it to reject only those expressions that will produce errors while allowing all the others through? And it turns out this is not possible. And the reason is the halting problem. If we have an interesting enough language, then here we can't decide what some complex expression ... here in the if will produce. If it produces true, we'll get a 1 back, and the program ends with 2. If it produces false, then we get a function back and we get an error. So because of the halting problem, we can't actually do what we would like to do, which is reject only those programs that go bad and keep all the others. So are we stuck? Well, the answer is we can't reject only the bad programs, but we can reject more. And a type system is a particular strategy for approximating which programs will be good and which ones will be bad. We don't write a full interp, but we write an abstraction of interp that just figures out roughly what kind of thing will come back. And this strategy lets us rule out some programs that are bad, but also forces us to throw out some programs that could be good. Like if it turns out that this really is a prime number, this program would work, but our type system is going to reject it because it says, well, there's a general category Boolean for is prime, but a general category for int or fun for the different branches, and so I don't know what kind of general category I'm going to get for all of these. Right? So the overall strategy, again, is that we're going to assign a type to each expression. That's this category or approximation of what the expression is going to produce without actually interpreting it. Right? So we have to approximate somewhere so that we're not actually interpreting, and a type is our approximation. And of course, in the case of if, the type of an if expression is going to be based on the types of its sub-expression. So there's a kind of recursive type checking that's similar to recursive interpretation, but does not try to get exact values up. Right? And that's our way out. So as long as we're willing to throw away some good programs, we can make sure that we throw away all the bad programs.